Hey folks, this is a lecture for the second assignment um, that has really just two topics in it. One is linear functions and the other quadratic functions. Um, those are sort of natural first and second places to go. So let's just get right into it. I'm going to show you a screen that keeps my smiling face in the corner, but lets me display stuff in a web browser. The reason we've got this is I want us to use GeoGebra a lot. And so that's the main GeoGebra screen. If you go there, you hit the Start Calculator button, it'll start a calculator. um, I've already done that, so this is what it looks like after you hit Start Calculator. Um, so yeah, well, let's talk about linear equations first, linear functions. Now, a linear function, I bet almost everybody, when you hear those words, your mind says mx plus b, right? You immediately jump into writing mx plus b. And you can do that in GeoGebra, which is kind of interesting to see how that plays out. Um, so here's where y is, at the bottom of the, I got the little keypad up. You can get rid of the keypad, but then there's another button to bring it back. So um, yeah, so y, the equal sign is over there next to the number pad. Uh, to get m or any other variable that you want to use, you have to get the keyboard into the alphanumeric version. So it's probably worth it to see how this keyboard works. A little bit like the keyboard on a lot of smartphones. You've got one thing that's numbers and a few special symbols. Then let's see, this one is, well, special functions that we're not actually going to be too worried about. This one's where you get letters. And if you need weird symbols, they come up on here, including some like math symbols, like the perpendicular sign, or you see the infinity button there. Uh, I don't, no, I can't say y equals infinity. Oh, here's the undo button, backspace. All right, so I wanted to write m and then times x. Come back to the original screen, x. You don't have to put in the time sign in this system. Some computer things require you to say what the operation is, but this one's smart enough to know that if you put two symbols next to each other, you mean multiply them. And there's b. And so nothing has happened yet. You have to say go. And the easiest way to do that is on this keyboard, there's a little button that looks like a back arrow that says do it. It's the return key. Um, all right, so look what happened here. We've got a slider up here. That one changes what m is. A little bit small. Let me see if I can expand it out a little. Yeah, there we go. So what's m doing? It's affecting the angle that the line is at. You should know that that's the slope of the line. So if I set m to exactly 1, that's a 45-degree angle on there. If I set m to 0, hard to do. Darn, it's really hard to do. Maybe I should type it. Okay. Just got to stop at the right. Oh, crap. There we go. I got it. Yeah. So m equals 0. That's a flat horizontal line. What about b? What is b control? It really is this point right here where the thing hits the y-axis. That's called the y-intercept. And right now that y-intercept is 1, but if we change b, it'll be some different number. Maybe 4, right? Um, it's also possible to actually get it to plot a point. Yeah, so uh, you have to find the right symbols for this. Oh, I changed it alphanumeric. So the parentheses are down there at the bottom of this collection on the left-hand side. You need, well, if I want to plot the y-intercept, that's where the x-coordinate is 0. Right? So I'll put in 0 as the first coordinate at this point, that comma, and I want b, the whatever the slider is set for. So go back to the alphabet here and hit b, and you see that uh, it's plotted a point. You may have noticed that b changed. I had it at 4 and now it's at 2.5. That's because I, I paused the recording for a second and changed things. So if things jumped on you, that was why. Um, anyway, yeah, so that's us dealing with a line. Now, from a from a sort of real world perspective, what are lines good for? It's surprising how much they're good for. You can plot almost any wacky function that you care to name, and if you look at it close enough, it'll look like a line. So yeah, let me try that here right here in GeoGebra. So we'll say y. Well, I don't want to use that y. Go back to the proper y. There's a difference between the y variable and the y letter. Watch out for that. Y equals, how about x raised to a power, to the third power, minus x, whoops, not like that, minus x to the, how about second power? Let's see. Oh, wait, there's a plain button for the second power. That was nice. Minus, how about 3 times x? Okay, got a weird looking wacky curve on here. I literally was just making crap up, right? So, but I got it to draw something. The point of, or the interesting thing about lines, and in fact, this is kind of what drives calculus, is if you zoom in on that sucker anywhere, it eventually is going to look like a line. Now, in GeoGebra here, we can sorry, use a single touch to move the screen and a pinch or a double touch to zoom in. Do you see how what used to be a curvy looking thing is now looking like a straight line? That's that's the problem, or that's the feature, actually, I should say, of most things in geometry. If you've got a mathematical function and you look at it close enough, it'll look just like a line. And well, that's really kind of the key to calculus. So how should we think about lines? Let me go back to not looking at that weird thing, but get the view of the line we were playing with before. I don't think having a slope of 0 is very smart, so I'll make the slope a positive number. All right, 0.5. The B here and the M have actual really important physical meanings, right? They tell you something. B is where you are when you start out. If this input axis X was actually T, it might make better sense to you. What's the value of the thing when time is 0? Maybe like right today. If today is time 0, then how much is my stock portfolio worth? And if I was talking about my stock portfolio, I'd be really excited if it looked like this line we've plotted, wouldn't I? It's going up. That is, as time goes forward, tomorrow it's going to be a few dollars more, and then a few dollars more. And so the two things that pieces of information we're getting there from B and from M are where we are at the beginning, at the starting time, and how we're changing. In this case, we're changing in a positive sense. If M there was a bigger number, it'd be even more exciting about if it were my profits in my business or something like that. I'd be really happy. On the other hand, if it was profits and I had something that looked like this, I'd be looking for where's the problem, right? If I have my profits right now are 4, I don't know what the units on that are. Maybe it's $4 million a second is what we're bringing into this company, but it's going down like that. In 5 seconds, it's going to be at 0, and that would be really, really bad. So you would hope that you don't have this kind of downward angle on your profit function, but sometimes you do, and that's actually one of the things we'll view a lot in calculus. All right, so that was me on lines. Let's go to a different view here, and excuse me 1 second. It's still getting used to the system. So this is basically a doc cam, so I can write on here. What we just talked about was the equation for a line y equals mx plus b. That has a name. It's called slope-intercept form. Which is probably the most unimaginative way to name something I've ever heard of. It's named for the things that are in it. M is the slope, B is the y-intercept, the intercept, right? So it's named for the M and the B. There are other ways to talk about a line. There's There's one that I really, really like a lot, which looks like this. Okay, that was a weird squiggle I made. It looks like this. Y minus a y value. Now, okay, we'll come back to that. Equals m times x minus an x value. I got to put in numbers that are a sort of an arbitrary x value and an arbitrary y value into there. People usually do this. They put a little subscript on it. So that's a y with a subscript on it means not the real variable y, but a particular value of y. And similarly, a real x value would be x0. I learned this stuff from somebody who was British, and he pronounced the zero as naught. So you may, I know I will occasionally slip up and say y naught or x naught. Um, just, well, I guess we should all be able to get used to that. Also, there's something a little bit wrong in what I've just written here. Do I really need the parentheses over here on the left? No, not really. So another version of this is to just scrub the parentheses first and then add y naught to both sides. So then it is really solved for y. Y equals m times x minus the x0 value plus the y0 value. Now, what is that for? That actually uses two other pieces of information. Instead of the slope and the intercept, it uses the slope and a particular point, x naught, y naught. So this is called point slope form. There are two different versions of it, but really they're both point slope form. So that has the slope m, and it goes through x naught, y naught. Did I just say the naughts again? Okay. I told you you need to catch me slipping up on that. Um, all right, there is one last version of a line, an equation for a line that is uh, very seldom used, to be honest, but it's here for completeness. You should note that how y has like a special role in these things. Y is by itself on the left side of the equation, except for in that one, and still it's all y-ish stuff on the left side. And basically everything's solved for y. This last form takes x and y and says, they're treat them equally. There's no x isn't special over y, and neither is y over x. So it just says, look, take some multiple of x and some multiple of y, add them up, and set that equal to a third number. And if you have a thing like that, that is actually known as standard form, although I think most people would think that the first one we did, y equals mx plus b, is standard form. Like I said, not used that much, but it's good to know it exists. What you would normally do with that if you had a line given to you in standard form is convert it into one of these other ones, which you can do pretty rapidly. I guess I should give you a quick example of that. Suppose I had the line in standard form, 2x plus 3y equals 7. What would it mean to convert that to, say, the mx plus b form? Well, basically it means solve for y. I would say I'm going to subtract 2x from both sides first, and then divide both sides by 3. I've just solved it for y. Well, now that I finished writing, I've just solved it for y. That doesn't necessarily look like mx plus b, but realize that the fraction there can be re-expressed as two fractions. So you can think of this as minus 2/3 times x plus 7/3. And once it's in that shape, right, it looks like y equals a number times x plus another number, then that guy is your m, and that guy is your b. Okay, let's do the other topic for today, which is quadratic functions. Now, in quadratic functions, the standard form actually is the thing that people tend to use most often. Am I right about that? Actually, I take that back. But we still are going to call it standard form. I think if we we really got standard form, it would scare everybody because it has 6 letters in it. Five, 6 letters. Oh, that was right. Uh, so, so yeah, what is a quadratic going to look like, or a quadratic function? First of all, the word quadratic has to do with squares. If you've heard the word quadrangle before, or even quad, I mean, people talk about the academic quad out between the Engelman and the library and the student center. It's not actually a quad because it's not shaped like a rectangle, but that's where the word comes from. Quads are generally rectangular areas. So rectangles, squares, they all have this Latin root quad in them. So that really means square. So when you say something's a quadratic, it means it's got x squared in it. Okay, it's not just going to be x and a constant, but it'll have x squared and x and a constant. The general form, oh, this is the word I was searching for before. General form for a quadratic is y equals ax squared plus bx plus c. Um, that's useful, but it's not really the best form of a quadratic. The best form comes from thinking about what we did in the last lecture, where we start with a basic thing. In this case, it's just going to be y equals x squared, and then we do stuff to it, transformations to it to make it look, how we want it to look. So the version I'm going to give you is called vertex form. And here's what it looks like. Y is equal to something times x minus x naught squared plus y naught. What's that going to do? Well, let's see that on GeoGebra. Okay. So can I just kill out this stuff? Delete, delete. Oh, it deleted it all. Cool. I'm going to probably not use x naught and y naught because I think that might be awkward. How about we use little a and little b as the names of the point we're interested in. Actually, you know what? First, kind of putting the cart before the horse. We should look at what does y equal x squared look like. Oh, yeah. Well, maybe we knew this already. It's a parabola. What I want to do first, I guess, is just move that parabola around. So I'm going to make a new function, and I'm writing it as an equation. It's y equals parenthesis x minus, let's go get a letter, a, and well, that's squared, and then plus, I need another letter, so I'm using a and b. Now this a and the b that I'm creating here, when I hit go, it's going to give us sliders for them. And watch what the effect of those. It's a little weird that the sliders start out at 1 instead of at 0. I would have kind of set them both to 0 if it was my choice, programming this thing. Well, I can't quite get them to be 0 because my hands are shaky. But let's get that thing out of the way. What does A do? Since I wrote it in there with a x minus the number, when I increase A, it actually moves to the right. Remember the last time we did x plus the number and then it moved the opposite direction where we're used to? This happens to be a smart way to counteract that. Okay, so I'm not seeing B. What happened to B? Oh, it just disappeared because I got it set at 0. It doesn't think it needs to write anything if I got it set at 0. Now for the B number there, I did write it as plus B, and so when I change the slider, like making the number bigger, it sends the curve upward. And when I make the slider move the number to a smaller value, it sends it down low. So this is actually kind of fun to play with, right? You can move that guy sideways. You can move it up and down. which means you can put one of those curves, a parabola shape, anywhere you want at all in the plane. You name a spot, you can put it there. Now, that's not quite what I showed you a second ago when I wrote vertex form. In vertex form, we also had a number out front of the x minus something squared. Let's see if I can insert that in here. Get my old keyboard back and go to ABC, but I'm going to capital A because that'll match with it. It's probably going to make the slider for me, I hope. Didn't like to make the slider. That's a shame. Is it just not like the letter I used? No, it's like it's done. It's already done with its slider creation, so it feels like it doesn't need to do it. You know what? The easy way to do is clear it all out. You don't need to save it and start fresh. Why? Gets to the 1, 2, 3 thing. Y equals capital A times x minus, get the letters again, little a. Let's put my cursor in the wrong spot. Sec to the second power, and then plus little b. This better work. Huh, that didn't work. I'm going to pause the video for a second and figure out what's wrong. Hmm. I think I'm back to talking to you. That's a little bit weird. It just really didn't like using a capital A for that. So I used A and B are the coordinates of the point, and the C is the number that's out front. If I make C bigger, look what it does. It kind of looks like the graph is squeezing in. Oops, sorry, I wanted to push it more towards the center. But what's really happening is it's stretching it vertically. The value of A, or what I'm now calling C, is a scale factor. It's something that scales the graph in the vertical direction. And if you make that scale factor negative, like going like this, you get upside down graphs. The A and the B, those are just pretty straightforward. A moves it side to side, B moves it up and down. This thing is called vertex form for a reason. That little spot right there, they call it an extremum, but on a parabola, that's known as a vertex. It's something you can always locate, right? That's the position. It's kind of like 0 is, or the 0, 0 position is when y equals x squared. It's got a lot of features to it. No matter If C is negative, it'll be the highest spot on the graph. If C is positive, it'll be the lowest spot on the graph. It's also where the graph is curved the most. You should notice that if you were riding your bike along something that looked like this is the spot where you'd be leaning hard into the turn, right? Over here, it's more or less straight, but in here, it's got a bit of a turn to it. Um, that's especially obvious when the C value is large. The A value is not. Right? It's very straight looking over out of here, but down there, it's got quite a lot of curve to it. Okay, so that's kind of a crazy introduction to vertex form. Sorry about the funny business with letters. I didn't know I couldn't use capital letters. Um, let's let's return to a different view, and then we'll call it a day. Basically, I just want to. Oh, sorry, trying to move my cursor in the wrong direction. Hit up against a wall. Uh, Basically, I just want to show how you might convert between these two things, and maybe one quick example of why we would want to use vertex form. Let's do the latter first. Suppose I knew that the profits for a corporation I was working at would be modeled with something that gave something like that. This is a this is actually intended to be a profit versus productivity graph. So this is dollars on the y-axis, and this way is units produced. Um, this is this is really typical of how such a productivity profit graph will look. Clearly, if you're not making anything, right, you're going to have negative values for your profit. And there's a spot right there where you finally have produced enough product, and we're assuming you're selling everything you produce, that you break even. You've heard of the break even spot. This is not always going to be the case, but in this, it's not untypical that you get to a sweet spot where you're putting out just enough stuff to make the most money. And if you try to go to higher productivity, it actually brings you down. You make less money. Why would that happen? Well, for instance, in order to make more things, you had to hire more people and you got to pay for their benefits and everything else. Their contribution doesn't really increase the net that much, and they cost you more than they actually produce for you. So you get a drop in profitability. It's even possible to start making so much of the stuff that you end up bringing your profit to zero. Now that's typically from another factor. If you want to sell that much of your junk, you got to set the price lower in order to get people to buy it, right? Supply and demand. If you drop the price, people will demand more of it. But then you're making less money per unit. And eventually you get to the point where you've sort of outsmarted yourself. You've brought the price down to a level where you can sell an awful lot of it, but you end up making no money. So this kind of a sweet spot is really important in there. So let's suppose I just wanted to make a mathematical model of this situation, and I knew that at 100 units of productivity, maybe it's 100 per hour, I'm maximizing my profit. Maybe the profit is here, and let's just say that's one. Okay. It could be $1 million. Could I make myself a graph that does that stuff? And well, the answer is pretty easy. Let's use the one we were just using. Let's transition back to the view of GeoGebra. Uh, well, I'm going to need to pinch a little bit. So I always remember forgetting which way to do for pinching. Okay, that's looking pretty good. I wanna see 100 on here, right? That's where the max was happening on that picture. So one of the things I'm gonna need to change these sliders a little bit. I want A there to be 100. I know that because, well, why do I know that? It was the x coordinate of the vertex. So now I just moved the whole thing over to so that it's near 100. You see that? So The thing's got the wrong shape though. It's curved upward a lot, and the thing I was after is curved downward and kind of not that much. So I'm going to need to change that number out front to something negative and not too negative. I'll get to that in a second. The other thing is B. B, I want to be 1, right? I want to reach a profit level of 1 when we have that sweet spot 100 units per. I can't see. All right, fine. 0.8. 0.8 will be fine. Now, I do want to see something. Let's see if I can make this happen, right? Yep. It's clear that my C value is going to be negative, but it's not going to be as big as -5. So I'm going to change that end of the scale for this thing to be like, I think -0.1 should do it. And I want the other end of the scale. Honestly, I don't want to have it anywhere near 5. I don't want it to be in positive territory at all. What's it want to be? There we go. All right. Did I just change that? Oh, good grief. Sorry about that. Well, you don't even notice the delay. I paused the recording for a second and I went through and figured out what the heck was wrong with it. And I probably should show you what I had done wrong so that you won't make the same mistake. If you go into the settings for that controller and click on slider on the top, what I needed was not just changing the min and the max, but also this one, the increment. And after playing with it a bit more, I found that what I needed was to make the min be negative, really tiny number, 0.001. And I made the increment much even tinier so that each pixel as the slider moves over moves the value of the variable there, C, by that amount. So then I also had to fiddle around with some settings to make the y-axis have a different scale on it than the x-axis. See how the x is going from 0, well, that 100 value is in the middle, but the y-axis, we wanted to be able to see a y value of 1 on there. Well, I never did fix this to be actually equal to 1. There we go. And this is more or less the picture we want. I think the C may be slightly off. I think maybe something like that is what I had drawn originally on the other screen. Let's take a look. Sorry. One day I'll get used to the transition there. All right, so yeah, that's not bad, right? That's the rough thing that I had, and this is what I've created in GeoGebra. And that means I've actually got a formula for something that all I had before was a sketch that you might put on the back of a napkin. And that's actually pretty handy, pretty useful. Okay, so that's it for today. We'll talk again soon.